In language, word order isn't just a detail, it defines logic. Swapping the subject and object transforms the entire context, meaning an effective model must track exactly where each word sits to capture the true intent of a sentence. Modern transformers gain their speed by processing every word simultaneously, but this creates a fundamental blind spot. Because tokens enter the system as a parallel set rather than a sequence, the model cannot inherently distinguish between a cat eating a fish and a fish eating a cat. This occurs because standard word embeddings only represent semantic meaning. Without spatial context, the vector for the word cat remains identical regardless of its role, leaving the model with no way to tell if it's the actor or the victim. To fix this, we need to inject a unique positional stamp into each embedding. Our goal is to create a mathematical signature that clearly defines a word's coordinate without destroying its original meaning. We might try simply assigning integers to each position, but this fails because the values are unbounded. In long sequences, these massive numbers would eventually dwarf the word's meaning, forcing the model to care more about location than definition. Alternatively, using one-hot vectors for position fails because they lack a sense of distance. In this setup, a word at position 1 is mathematically just as far from position 2 as it is from position 1000, making it impossible to learn local patterns. An ideal solution must be unique, deterministic, and bounded. But most importantly, it must be smooth. Nearby positions should have similar signatures so the model can naturally perceive the relative distance between tokens. This leads us to sinusoids. By using sine waves, we ensure the positional data stays perfectly bounded between -1 and 1, providing a predictable range that doesn't overwhelm the semantic logic of the word itself. However, a single wave eventually repeats. This periodicity creates ambiguity, because different positions could end up with the same value. To create a truly unique identity, we need something more complex than one simple oscillation. By layering multiple frequencies together, we create a high-dimensional fingerprint. This combination ensures that every step along the sequence has a one-of-a-kind signature that can be reliably decoded by the attention mechanism. The specific formula uses alternating sine and cosine functions across different dimensions. By varying the frequencies from rapid pulses to slow, sweeping curves, we span the entire embedding space with mathematical precision. When visualized as a matrix, these waves form a global coordinate system. Each column becomes a unique high-dimensional fingerprint, turning the sequence into a smooth mathematical landscape where the model can easily navigate. The hidden genius of this approach is that it treats position as a rotation. Because sine and cosine define coordinates on a unit circle, moving from one position to another is mathematically equivalent to a linear transformation. This rotational property allows the attention mechanism to learn relative distance. Since the shift between two tokens is consistent throughout the sequence, the model can easily recognize the same relationship whether it happens at the start or the end of a sentence. Finally, we combine these two worlds by adding the positional vector directly to the word's meaning. This simple addition merges what the word is with where it is, creating a single context-rich input for the transformer. With meaning and position unified, identical words now have distinct vectors. This elegant math allows transformers to keep their parallel processing speed while maintaining a perfect sequential understanding of the world.